Okay, all right. Okay, let's get started. So first thing is a little about the homework, right? So on the homework for the last question, question 6, basically the question is quite open-ended. And I got many emails asking me, what do I want out of that question? Basically, the question says you have a wind turbine, it's generating, power according power as a random variable, and you have a battery. How will you operate the battery? Right? So the idea is for you to think through this question. Right? There is no right answer. Certainly, there is unlikely to be a closed form formula you can derive. So this is not that far from practice. So nowadays, many utility or many facilities managers and people in the space is often you get donated a battery. Right? So this has happened to us. And somebody who has a battery, who doesn't know what to do with it, or have used a battery for some other testing purposes and wants to donate to you. So you get a battery, and the question is, okay, now what do I do with this battery? Okay, so, and there's no industry standard rule, for example, to determine how the battery is used. Okay, so it's a case-by-case basis of giving your uncertainty and how you want to use the battery. Okay, so that question, you want to attempt that question, right? So now think about if you are managing this wind turbine and somebody give you a free battery. So if you have a free battery, then of course you have to design a route, when to charge the battery, when to discharge the battery, this kind of route. So how will you design the route, and what kind of consideration do you think you want to take into account? Right. So the idea is not to have a closed form formula, have a proof of this is the optimal route, but just for you to walk through your mind. If you have battery, how you operate the battery. Okay. Right, so this is the idea of the question, is for you to explain a little bit, what your rule is and what your thinking process behind the rule is, and why do you think is a reasonable rule. Okay, right, so I'm not looking for a formula, but more for if you have a battery, how you operate, okay, and why is it reasonable. Any questions about that? Okay, right. So that's the idea for the last question, is try to think of a reasonable strategy, right, and explain why you think it is a good strategy. Okay, so that's the first order of business. Second order of business is, so we need to pick a midterm date, right, for the midterm. So as a reminder, so midterm is what is a day long, so take home. Take home, you can think of this being, so this is a full day. Right, so it won't happen over, it doesn't have to happen, over the class times, right? So, so some possible dates are, looking at the calendar, let's say February 9th or 11th. Right? Those are possible days. So that's a Tuesday and Thursday. So if we set it on, let's say, the 11th, February 11th, any objection to that date? Any conflict that I should know of? The chat, there's a question in the chat. Does anybody know when 458 is? When the exam for 458 is?
Yeah, I think we have 458 lecture on that day.
Yeah, so we're not going to avoid the lecture, right? So no matter when we start the midterm, we're going to conflict with the lecture. So the thing that we want to avoid is not another midterm on the same day. Right? So lectures, there's no way we can avoid those conflicts.
Around how long should we have put aside for this?
So you have a full day, right? So I'm gonna probably post it, very early in the morning, and you have it until midnight. I would think this, so my target is to have this around 2.5 hours, so close to what you would have in class.
Okay.
Yeah, so it's not. I don't anticipate you spending, 5 hours on it, right? So
Yeah.
I don't anticipate you having to spend 5 hours.
Yeah, I have like 6 hours of class that day, so as long as it's not
Yeah.
gonna take me all day, that's fine.
Yeah, so there's no way. This is every day. There's whatever day we set it on will be 6-hour class on that day. So that's
Sure. Yeah. As long as it just isn't designed to take all day, because I know some of the tests last quarter took.
Yeah, so this is not designed to take all day. You can think of this, as an exam you would do in class. Maybe it was a question suitably modified. So, taking into account that you can Google, right? Or you can use your computer. But that's the idea for exam. We'll have regular lecture. So the lecture I will convert just to an office hour. If you have questions for the exam, you can ask. Right? So we'll have no lectures. Right? So the idea is post-exam early in the morning, you can have a chance to take a look at it. By the regular lecture time, you can ask any question that you have. Okay, so any concerns? If not, I think my sharing dropped again. Okay, give me 1 second. Okay, so if no concerns about this, so we'll have it on February 11th. Let's say from 5 a.m. to 11:59 p.m. Okay. The lecture is used to answer questions. Right? Okay. So we're gonna use this. Right. So we're gonna use the lecture as a question and answer for any issue you may have. Otherwise, we'll just have this. We'll have the midterm on that day. So again, the difficulty will be similar to the homework questions. The length will be between 2 to 3 hours. It's open, right? As long as there's no communication between you guys, then everything else is okay. Right? You can Google, you can ask other people as long as these are not people in the class, right? So you can use computer programs, you can use whatever you want for this one. Right? Any other questions, concerns? Do we practice? Yeah, no, there'll be no practice exam. So you can think of the homework as a practice. You want to make sure you can do all the questions in the homework in a reasonable amount of time. Any other questions? Okay, so one note about the lecture being used to ask questions. So that will be converted to a case where it's a waiting room and one person at a time. The reason is, from last quarter, often people want to show me what they're doing, right? Since I can't see it, it'd be easier for people to just show me what they're doing and ask me, are they on the right track or something like that. Then obviously it's not possible to have as a regular class where everybody can see the screen. Okay, so for that day, plan to ask your questions, but don't. It's not a place where you can hang out, for 2 hours and ask questions in case you have them, right? So we'll run it as an office hour, where you ask question. If you come, you ask for a question, then you log off, and you need to ask question again. You go into the waiting room again. So it's not a sort of open setting. All right, so. Okay, so no objections. We'll go with that day as a midterm. Yeah, so we'll get, by the time we're closer, we'll know exactly where we end. Okay, so we'll decide the topics covered once we're closer to that date. Okay. All right, good. Okay, so today, going back to the class, we will cover, as we'll basically cover induction generators. Okay, so induction generators, this is a Easting type 1, 2, and 3 turbines, right? So it's quite common. So we're all over the place. So we're going to today basically as more of a review of induction generators. We won't be seeing all that much new from, say, the last time you saw induction generators in 351. That being said, there's a lot of equations in induction generators. So I want to go through them, somewhat carefully. And because you see a lot, like will be every, for 1, 2, or 3, it will be just a modification of the equivalent circuit. So I'll do a review of induction generators and remind ourselves what are all those equations, what are different powers, what's torque, and things like this. So induction generator, we all have all seen this, is a very simple generator. Not much can go wrong, and not much can, it doesn't sort of very easy to construct, quite easy to construct. So the good thing about induction generators is, right, so there's the easiest technology to use. Since they're the cheapest ones to make, they're very reliable. The generator itself, is super reliable. There's not many parts that can go wrong. Okay. Their power density is quite high. Okay. So the weight to power ratio, or the power to weight ratio is quite high. Okay. So it's a very cheap, simple motor to use. It's reliable. And that's the first generation of turbines. That's why they use induction gen. Right? That's why they use induction machines as generators. So to remind ourselves, how do induction machines work? The idea is quite simple. Right? You have a rotor in the middle, and you have stator outside, and you pass a sinusoid current. Okay, so this thing works because there's a sinusoid current going through. Right, so we're going to pass three-phase current. So we have three-phase time-varying current. Okay, we're going to have three-phase current. So for induction generators, we'll always be talking about three-phase generators. Okay, even if the circuit diagram shows a single-phase equivalent, also remember that for these generators, we'll talk about three-phase, right? So what happens is basically sets up a rotating magnetic field. In the air gap, and this turns a rotor. Right? So this is what turns the rotor. For a turbine, in the rotor will turn the shaft. Then right, so in the turbine, this is run backwards, right? So you have a shaft that's turned because the blades are turning, and this way will generate power, right? So that's our induction machine. So again, we have a changing magnetic field, and from this changing magnetic field, we'll have a rotating. Basically, this produces a rotating torque. Okay, this will produce rotating torque. So none of this should be a surprise, right? So I'm assuming we'll have also induction motors, right? So these will go relatively quickly. We'll slow down when we get to the equations, but this operating principles will go through quite quickly. So we have sort of this rotating field, and what happens is this field rotates in time. Right? So this is a field that rotates in time, and this turns. Right? So that's the mechanical power right? This extracts the mechanical power from the this extracts the electrical power from the mechanical power as turning the rotor. Anyway, so and again, all of this for this kind of machines, there's no difference between a generator and a motor. There's no difference. Whether it's generating power, consuming power, is basically determined by whether it's faster than the synchronous speed or slower than the synchronous speed. Okay, so that's what determines whether it's generating power or consuming power. Otherwise, there's no difference at all for this kind of machines. All right, so finally we get to the rotational speed. Right? So we have this rotating field. This creates a flux in the air gap, and we have idea of one AC cycle. Right? Basically, every cycle we turn once. Okay, we turn once. Right? So let's introduce a very important notion of the synchronous speed. Okay, so let's introduce the idea of a synchronous speed. A synchronous speed. So as a reminder, question is, if the machine is turning exactly at the synchronous speed, what happens? Is there a power exchange if the machine is operating exactly at the synchronous speed? Right, so the machine is operating exactly at the synchronous speed. There is no power exchange. Right? So that's why it's the synchronous speed. This is really the frame of reference we think about things. Okay, what this gives us, this is our frame of reference. Okay, this is our frame of reference. Basically, you're going to think of the machine, a machine turning at synchronous speed as basically a machine that consumes zero power. It's a machine that is operating at equilibrium. Right? It's not consuming power, it's not generating power. Okay? And the synchronous speed is given by basically the AC cycle speed. Okay? So for a machine in the United States system, it will be 60 Hertz. For a machine in the Europe, will be 50 Hertz. Right? So this is the synchronous speed of the machine. Okay? So number of poles, right? So we have the synchronous speed, but then we can add poles to the machine. So what does adding poles do? So what does adding poles do, right? So we have a machine, right? So I have a rotating field. I can basically have because my rotating field is going at 60 Hertz. So I have some speed that's, for example, this is 60 Hertz, or here is 3600 RPM. Okay. So if you take the grid as a synchronous speed, you have a machine that turns at 3600 RPM. That's the machine we have. Then why do we need poles in the machine? Right. So this is a two-pole machine. Why do I have poles? Right, so what does the number of poles do for my induction machine? Anybody remember?
Changes the output frequency.
No, so we don't really have a well-defined notion of output frequency per se. Right. So what frequency does change? So what frequency does the number of poles change? Okay, so so if I connect my machine, if I have a single pole machine, I connect it directly to the grid, then the synchronous frequency will be 3600 RPM. 3600 RPM. For big machines, right? It may not always be easy for them to rotate at 3600 RPM. Okay, think of the size of wind turbines we have seen. Okay, so, even with gearboxes, it may be very hard to get a machine to rotate at 3600 RPM. Right? So we want to change the synchronous speed. Remember, the synchronous speed is our reference speed. Right? So we want to basically make the system reference speed a little bit slower. Right? So So adding poles is basically changing the synchronous speed, right? That's why we add number of poles. And we want to change the synchronous speed is because 3600 RPM is sometimes too fast. Okay, so imagine, what the normal turning rate for a wind turbine blades are. Right? Those are nowhere close to 60 hertz. Right? Even the wind turbines in a very high wind does not turn anywhere close to this. Then if your synchronous speed is 300 RPM, and all you're doing is you rely on your gearbox to shift to this kind of speed, that's very hard, right? Sort of very, it's not easy, not trivial. The idea is we can slow down the synchronous speed, and the way to slow down synchronous speed is to add poles, add a number of poles. So this changes synchronous speed. Let's change the synchronous speed. So why does it change the synchronous speed? Well, the reason they change the synchronous speed is you basically have to rotate twice to see one complete picture. Okay, so we have more poles. Basically, if you only have one sort of AC pole, you only have one three-phase circuit, then every AC rotation, you're symmetrical for every AC rotation. Now, if you double this, basically you need to rotate twice in the AC current for all the coils to see you once. Okay, so the symmetry basically is you're reducing the number, you're increasing the number of AC cycles you have to see for the machine to do one complete rotation. Okay, so this slows it down a bit by adding more poles. Right, so this slows it down. So that's why we add poles is that's too fast, we want to slow it down. So the equation, which you should all have seen many, many times in 351, is this equation. So the synchronous speed is 60 times Fs. This is the grid frequency, so 60 hertz, divided by the pole pairs, number of pole pairs, or 120 times the grid frequency divided by the number of poles. Okay, so this equation shows up again. This equation will show up again and again. Right, this will show up. It's very common for this equation to show up. Okay? So this is a good equation to remember. The impact of the number of poles on the synchronous speed. Any question about this equation? Any question about the number of poles? Impact number of poles? Okay, so can I speed up the synchronous speed? Can I increase the synchronous speed? Right, adding number of poles decreases the speed. Can I increase the speed? So you have a washing machine and you want to turn faster than 60 hertz. Can you increase this? Right, so I can decrease it, right? That's certainly fine. Can I increase this?
Would you stop powering a set of poles?
No, because this is balanced three phase, or assuming balanced three phase, it's very hard to stop power going somewhere. Right, so this actually is highly non-trivial to speed up the synchronous speed. That you probably have to do, in the old days using gearboxes. Nowadays we have electronics. Okay, so speeding up is not easy. Okay, so we're adding poles, we can slow it down. And the way we slow it down is also we cannot slow it down to any arbitrary frequency, to arbitrary speed, right? So remember, so the possible speed. So we have 3600 RPM. This is certainly possible. This is a single pole. machine. This is sort of a one pole pair or one pole machine. What is the next possible speed? So why is it 1800? What happens in the middle? Can I achieve, say, 2500? What if I want 2500? What if my application just runs better at 2500? Can I achieve that speed?
Doesn't it all have to be a multiple of 60?
Has to be multiple of 60 and has to be 3600 divided by even number. So it works this way. This is 1200 and so on. Right? So this is 36. So this one, this is the step. This is the first one to start with. This is 3600 divided by 2. This is 3600 divided by 4. Okay. The reason is we're going to think of pole pairs, right? So poles come in pairs. So you have to divide by an even number. Okay, so there are two pole pairs. There's sort of two pole pairs, or right. So the poles come in pairs. So it's 2 pole machine, 4 pole machine, 6 pole machine, things like this. Okay. So there's sort of a defined set of synchronous speed this thing can operate on. Right. So you're limited, basically, you limited to operate at discrete speed. So this is also a fixed speed drive. This in some sense is a fixed speed drive because you cannot basically arbitrarily change your synchronous speed. Okay? We're very limited by the synchronous speed we have. Okay? So this is again where, for a few decades back, when you design a motor, you're limited by the synchronous speed. You need to pick one of them and go with it. Okay? Whereas nowadays, once we have power electronic drives or have more advanced drives, you can do variable speed drives where you're not limited by the sort of discrete, discrete list of synchronous speed. Okay? But this is something to keep in mind. Right? If we're just looking at induction machines, it's not possible to achieve arbitrary speed. There's not that many speeds to pick from. Okay? So if any of you goes on to take machines and drives as a capstone, or have taken that, or is taking that right now, you basically see how to sort of make more advanced drives. Any questions about this, about the poles and machines? Okay, right. So this is our calculation of synchronous speed, right? For almost every question, you need to figure out what the synchronous speed is. Okay, so this is definitely a useful equation to remember. Okay. So we'll do a little bit of review, right? Of how do you generate power, basically. Right? So again, remember that at synchronous speed, there's no power being exchanged. Okay, so you have a motor that's if your generator rotating at synchronous speed, nothing happens basically, right? It's sort of a zero resistance wire, something you can think of that way. Okay, so how do you develop power, right? Well, where does power exchange coming from? All right, so at a very simple level, right, power exchange comes from Faraday's law. Okay, so we have a flux, we have a conductor moving at the flux to generate voltage difference. Okay, so what this is saying is, so what you can think of, the key thing to here is, the key word we want to read here is the relative velocity with respect to field velocity. Okay, so this is what Faraday's law is saying. Okay, so if you remember, if things are rotating at a synchronous speed, and if the motor speed if these two are exactly equal, then relative to each other, there's no motion. Okay, where they are moving through a flux, there is sort of magnetic flux. They're moving through a field. But the field is moving at a synchronous speed, and you're rotating at synchronous speed. so there is no relative motion. Okay, so Faraday's law tells us if there's a relative motion between the field and the conductor moving through the field, then you can produce some voltage. Okay, you get a voltage difference across if there's a relative speed difference, right? So this is the this is relative speed difference, right? So this is how we generate voltage. This is the voltage coming across. Then I can produce a force if there's current through the conductor, right? You can think of, there's a relative motion. I create some voltage difference. This leads to a current difference. Then this moves the conductor. Right? This moves the conductor. Okay? So this is the idea of why you need to move sort of relative to the synchronous speed. Okay? Right? So you need to move relatively to the field. Right. So the rotating version of Faraday's law, right? So the rotating version of Faraday's law is instead of v, linear velocity, we're going to think of this as the angular frequency, right? So this is the speed of rotation we have. And instead of force, we're going to think of torque. But the idea is the same. So if the idea is to move relative to a rotating frame of reference. Right? If there's relative speed difference, you generate some voltage you can think of. And then this voltage generates current leads to force. Okay? So this is Faraday's law again. Faraday's law. Okay? So then basically the way we generate power or we consume power is you apply a three-phase, right? Three-phase voltage to the stator. This sets up, this creates a synchronous speed. Right? So they apply this creates synchronous speed. Then the field rotates in the air gap. Okay, that sort of induces this rotation, field rotation. And the idea is you want to have a delta n, right? You want to have a difference. You want the rotor to be at a slight difference, some difference in the synchronous speed, and this way the motor will rotate. Okay, so that's the way we get motor to rotate. So once the motor rotates, right, either consuming power, right, but either this from consume mechanical power or this generating electric power. Okay. So that's the very simple version. This is a very simple version of the Faraday's law and why induction motors work. Okay. So this basically says, again, if the relative speed is 0, nothing happens. Okay. There's nothing happens to this machine. So you want to be different than 0. So all this is saying is, if you're running this with a motor, you want to be different, right? You want to be different than the synchronous speed. And the motor speed is basically given by the load torque, okay? By the load torque. There's some function, we'll get to this function. Okay, we'll have an equation for this function. But we'll get equation for this function, but the idea is, depending on the load torque you have, this determines what the speed difference is. Okay, so if greater than 0, then this will be greater than 0. Right? So if I'm powering a load, I'm slower than the synchronous speed. So this means I'm a generator, then delta n will be less than 0. Okay. So it's possible to be slightly faster, right? You can run slightly faster than synchronous speed because you're generating power. So you generate power if you're faster than synchronous speed. Any questions so far about this? Okay, so this is the synchronous speed, right? So if you look at the equations, if you recall from 351 or equivalent class, then we talk about slip, right? So slip is a normalized measure of the difference of the relative speed to a synchronous speed. Okay, this is sort of nothing. That's just more convenient to using equations. Okay, to think of a slip as a fraction, right? Think of the speed difference as a fraction of the synchronous speed. Okay. So what is the normal range of slip? Anybody remember how big or what's the sort of the magnitude that slip can take? Will you expect to see a slip of 0.5, let's say? All right, so anybody remember the reasonable range for slip? Right. Okay, so slip normally, the magnitude slip is small. Say, less than 0.1. Right, definitely less than 0.15. Okay, so slip is operating over a quite narrow range. Okay, so if you ever get a machine the slip is 0.05, run away very fast from the machine. Okay, so this motor is only stable, right? So there's just a stability concern, and the slip is kept very, very close to synchronous speed. Okay, and if you recall, that's why type 1 was quite restrictive. It was quite restrictive as a turbine, right? Because you just directly use induction machine, then you basically can only operate a very narrow range. Right? You can only operate a very narrow range away from the synchronous speed. Okay? That's why type 1 was limited. And we'll see, so we'll have a better mathematical idea of why the slip is so small, right? So why can we not operate a slip very far away from 0? Okay, so we'll see that later. We'll see that maybe the second half of this class. Okay, but now it's as to remind yourself, this is the equation, right? This is the equation for slip, and slip generally is not very big. Okay, so close to 0, positive or negative. Okay, so this is again repeating the idea, just a picture of the slip. Right? You have a rotor, we have a stator, and there's a difference between the air gap rotation speed and the rotor speed. Okay. So if you look at the induction machine, right? So what is the induction machine? Right. So the idea now so what we want is basically what you really want at the end of the day is to derive this equation F. Okay, so goal of induction machine analysis is basically to get this function F to have a functional form, so we can use it. Right? So we can have equations and formulas to calculate stuff. Okay? But getting to this function F is by no means simple. It's by no means simple. Right? So if you recall what the machine actually looks like, right, it's something like this. Right? You basically have a bunch of coils wrapped around the stator and the rotor. Wrapped around coils. So if you have a bunch of coils wrapped around, right? You have sort of coils wrapped. What that looks like an inductor. Okay, so what happens is you have a bunch of coils, right? What happens is you have the coils on the stator, those look like an inductor. You have coils on the rotor, those look like an inductor. So our analysis of getting the actual equation is basically you have to look at what happens when those sort of inductors rotate against each other. Right, so that's basically the idea. You have a stator that's stationary, you have a rotor that's rotating. Electrically, well, you can view this as inductors. That's a set of 3 inductors, stationary, another set of 3 rotating. Okay, this is the picture, right? So you want to look at, so the analysis is looking at the angular frequency of things and analyzing what happens when you have a bunch of rotating inductors. right? So the circuit diagram is something looks like this, right? Basically, the stator, you have a three-phase. In this case, think of a Y-connected circuit. In the rotor, you have a three-phase Y-connected circuit, and then you rotate, right? There's a speed difference between the rotor and the stator, and the air gap. Right? So you have this kind of circuit diagram. You set up this kind of circuit diagram, right? So we basically have 6 elements we have to look for, right? When you do this kind of circuit analysis, you want to look at what happens for the current through each inductor. So there's current through each inductor. Okay. So there are 6 of them, right? There's 6 of them. So if you do this analysis, you're basically, what you end up worrying about is what this matrix look like. Okay, what you worry about is, okay, what does this matrix look like? Because I have 6 of these things, right? So I care about what is the inductance between myself and this neutral, that's L11. What is the inductance, say, between myself and, let's say, 2, right? A1 across 2, this L12, and so on. So you have a 6x6 matrix that characterizes how the inductors interact with one another. Okay. Basically, there's 6 of them. So there are 6x6 matrix of things to track around, right? To track, to see how they behave. And you want to see how these things change if, once we give in a rotating frame reference. Right, so you have all this, basically you have all this inductances you have to worry about, right? So there is right, so if you look at the machines class, you will work out this, actually. This is a good exercise to work out. It is good exercise to work out. Because it's actually, so let me ask you, right? So if you're doing this analysis, now you get to this 6x6 matrix, what would you do? Right, so imagine you're Tesla, right? So you invent, okay, so I don't think Tesla care about this, but Tesla invented induction motor, and so this thing works. Then people after Tesla wanted to understand, right, why did this thing work? What exactly is going on in this induction motor? Then you get to this point. Then what do you do once you get to this point? Right, so if you're taking, let's say, electrical engineering in the 30s, this is a lot of classes will be devoted to this calculation. Okay, so that was a big, say, very important topic at the time. We're not going to do this in any detail. Okay, we're not going to do this in any detail. We're going to basically skip a lot of this and present the final result. But before we get there, maybe it's good to spend some time thinking about it. As getting here is not hard, right? Because you draw the diagram, okay, there's 6 inductors. You write down this matrix. This is sort of the natural matrix right there. The crux of the matter is what you do once you get to this matrix. Okay, there's 36 numbers here, and to keep track of all the 36 numbers, right? So any suggestion, any ideas of what to do here? Okay, any idea, right? So again, if you're a student in the 1920s and 30s, this is you go through this many times, right? So let's think about, right? So let's do some, we're not gonna do the math, but we can think about what possibly simplifies this. Okay? Does 3-phase help us in any way? Right, so I can write down this matrix. I can always write down this matrix, actually. This matrix exists, right? No, 3-phase or not. I don't need balanced 3-phase to write down this matrix. I always write it out. But let's say I write down this matrix, and now I'm given a balanced 3-phase system. Does that help? Okay, so what balanced three phase does in this kind of matrix is, so we have to analyze this matrix. Right? At the end of the day, we have to analyze this matrix. So balanced three phase simple makes, what this does is this creates symmetry. Okay, remember, for the same reason, we can work with balanced three phase using a single phase equivalent. Right? We said, okay, all the phases are the same. We don't care which phase we work on, just multiply things by 3. Okay? Same thing happens here. Okay? So if we assume things are balanced three phase, this 36 numbers is not distinct anymore. A lot of them are exactly the same. These are, we're looking at balanced three phase. So this is one thing that makes the math quite a bit easier. Another thing that makes the math quite a bit easier is there's something called a DQ transform. This is a fancy word. What this does is basically, this is the change of variables. Okay, what this change of variable does, this gives a diagonal system. And this is actually quite, so the idea of this analysis is basically saying there's too many numbers in this matrix. I can't, I don't want to understand. I can't work with all of them. Okay. The two ideas is, one, you have balanced three phase. Second, there is something called a DQ transform. Basically, if you think about the basis of this matrix, if you think back linear algebra, you can do a change of basis. Under this change of basis, you can diagonalize the system. Okay, it basically goes from a full 6x6 matrix to a diagonal matrix. Then what happens is also because it's balanced three phase, the diagonals are all the same because it's balanced three phase. So you can go from this sort of full analysis, doing some math, to this kind of equivalent circuit. Okay, so at the end of the day, that's sort of the story. As if you go through this, right, instead of going from a seemingly very complicated 6x6 system, right, we end up with the equivalent circuit, right? So you end up with the equivalent circuit because the DQ transform diagonalizes the system. Okay, there's a diagonal transformation of the system. Second is there's balanced three phase, so you only have to care about one of the phases, right? So you end up with a single phase equivalent circuit. Okay, this is our single phase equivalent circuit. All right, so we are going to not worry too much about the math of how do you go from here to here. If you work through it, and if you're up to date on your linear algebra, it's actually quite an interesting calculation. It's not that hard, actually. It's not that hard. It's sort of everything sort of pops up on its own. Everything pops up on its own. Okay, so if you look at the slides I have uploaded, at the end of the slide, we go through all of them. So there's sort of a complete lecture on DQ transformation, basically. Right? So we'll do a DQ transform. We'll get to this equivalent circuit. Okay, all these numbers will be well defined. Okay. We're going to skip that. We covered that in previous classes, but that takes about a lecture or more to go through. So this time we'll save that time and we'll basically cover more about storage at the end. Okay, so it's a trade-off. It's a trade-off, right? So if you're interested, please take a look at the slides we have. And any questions, I'm happy to talk about. It's actually quite a neat transform, right? It's actually quite a neat transform. And if you do power electronics, it's sort of, you do have to know the DQ transform in some detail. Right? But for this class, we're going to say that, for reasons, these two reasons, basically, things are equivalent circuit. And at a high level, it's just because there's a change of basis. It turns out there's a natural change of basis we can use. discovered in the, I believe, 20s by Park. Okay, so, right, so let's stop here. Let's take a break until 1:30. Right, I'll take a break at 1:30, then we'll go into this kind of equations and work through some examples, remind us what these things are and what are the quantities when we look at induction machines. Right. Okay, so let's resume at 1:30. So any question about homework, go ahead and ask. All right, okay, so let's get started again. All right, so from now, we'll be working with this equivalent circuit. So our circuit will be, if we see an induction machine, this is our circuit we'll work with. So most of these notations in the circuit should be fairly familiar, right? Should be fairly familiar to us, right? So this is, so the induction machine is basically a transformer, right? This comes from being a transformer with a variable resistance, okay? With a variable resistance. So this variable resistance shows up, this variable resistance shows up in as a basic variable shows in two places, where one there's R2 prime over S, the second is over injected voltage VA2 prime over S. So the reason for the prime on things like X2 prime, R2 prime, VA2 prime, IA2 prime, right? There's a prime for this because is that a transformer circuit. Okay, so this comes from the fact that you can model it as a transformer circuit. Okay, so there's an air gap, so you can think of this as being a transformer circuit. Normally, the turns ratio is close to 1. Okay, normally turns ratio close to 1. But just to be consistent with transformers, we'll label things as a prime, right? So anybody remember what prime for? What does prime denote? Remember in your transformer, what does prime do? Right, yeah, so reference to the primary, right? So for this kind of circuit, we'll always reference to the primary, right? So to be consistent, we'll write a prime, okay? We'll write the numbers coming from the secondary with a prime, okay? So this is our circuit. And this is the motor. This is a motor because S is larger than 0. It's a motor because S is larger than 0. So the resistance here is positive. Okay, we have a positive resistance. So to get the generator, everything stays the same, but S is negative, right? So the slip is negative. Everything's the same except the slip is negative. So if you look at this, for example, R2S over S, this is negative. Okay, so we have a negative resistance, right? So a negative resistance is basically something that generates power. So you can think of it this way, right? That's where the slip enters into the picture. Okay. Everything else stays exactly sort of the same as before, except that power now flows from rotor to stator, right? So this is power flow, whereas in this case, this is power flow. Okay. I just reverse the direction of power flow because now I have a negative resistance. Okay, so something that raises the voltage, right? Something that produces power. Okay. Right, so of course this is not physical, right? It's not physical, but just an equivalent circuit representation of mechanical power coming into my generator. Okay, so it's not really saying there's a resistance that's negative. It just is the equivalent circuit form. Right? Any questions about these equations? Right, so you'll see a lot of this. You'll see a lot of these equations. Okay, so the often is easier notation-wise to separate out R2 prime over S into two parts. Okay, into R2 prime plus RD. Okay, so R2 prime, this is just a rotor resistance. Okay, so this is sort of, you can think of the physical resistance in the rotor. Okay, this is the wire resistance if you want. RD is a developed resistance. RD is a developed resistance, and this has to do with the slip. Okay, this is something that has to do with slip. It's basically R2 prime over S times 1 minus S. Okay, so if S is negative, again, this is a negative number. That's a negative developed resistance, meaning that, again, we're generating power. So looking at this picture, right? So let's do a sanity check. So what happens when S is 0? Let's do our sanity check. What happens when S is 0? Is it true I generate 0 power out of the circuit? So if S is 0, what's RD? Is RD 0 if S is 0? Right, it's R2 prime over S times 1 minus S. So if S is 0, what's RD? Right, infinity. So what does the infinite resistance mean? So a infinite resistance is a what circuit? Is an open circuit, right? So S being 0 creates an open circuit. So that makes sense because for open circuit, there's no current flowing from the rotor. Right? There's no current flow. Right? So you have 0 power being generated essentially. So S being 0 means the developed resistance is infinity, means my circuit is open and nothing's happening. Okay, so that makes sense, right? That's a sanity check we do. Okay, so at least from that makes sense. Right? So this is the equation to remember, right? So this is the important terminology to remember, right? Developed resistance. So you will see many questions that asks us what developed resistance is. Okay, so these are just basic terminologies, right? So again, this is our generator model, right? So our generator model. So for our generator model, what do we want to think about this, right? So this is a negative resistance. Right? So RD is less than 0, so this is negative resistance. Okay, so this being a negative resistance is fine mathematically. Right? There's nothing, you can still do all the calculation you want. But sort of easier to think of the generator. So it's often more convenient to not thinking as a negative resistance, but thinking of this as a voltage source, as a sort of voltage, right? So this it increases voltage when current flows through it. So this increases voltage. We can think of this as a voltage source. It is called a current control voltage source. Right? Basically, it's a negative resistance, but right? So it's easier to think about this being a voltage source, Okay, and the idea of thinking about this as a voltage is now to think of this as a part that's providing power. Right. So if you have a wind turbine, in the system, then you can think of the rotation of the blade creates a voltage in my equivalent circuit. Okay, this voltage has a current flowing out of it, and this current and the power delivers is this power. Okay, so this is the developed power. Right? So you can think of this as the power that my rotating blade, and after the conversion in gearbox and so on. So this is the rotating mechanical power creates this much electrical power here. Okay, so this is the developed power. Developed power. Okay. So that's why this developed power is equal to the developed torque multiplied by the speed of rotation. Okay. So it's either, so sometimes it's better to think of this negative resistance, right, as a voltage source that's putting out PD. The amount of power is putting out is PD. And this is a conversion between the developed torque, T of D, that's coming from the mechanical torque, multiplied by the rotation speed, right? So this is the mechanical power equal to the electrical power developed as the rotor. Right, so if you look at this equation, again, this number is positive, but S is negative. So -3 times this thing is a positive number, right? Is a positive number. Any questions about this equation, about this sort of generator model? So you'll be very often again asked what the developed power or the developed torque is. Okay, this is actually an important equation to know. Okay, this is an important equation to know. Okay, you'll be asked this very often. Okay, for example, on the midterm, for sure you'll see a question asking you what the developed torque is or what the developed power is, right? So important equation to know where to find it. Okay. All right, so this is the equation, and so let's do some examples. It really is actually there's not much to be said. No, this is equivalent circuit, so all the equations are not terribly difficult, right? This is a linear circuit analysis. There's some inductors, some resistors. So let's do some examples to refresh our mind. Okay. All right, so then in this example, we're given the equivalent circuit. Right? Basically, we're giving this equivalent circuit. We're given that X1 is 2 ohms, X2 is 1.5 ohms, Xm is 10 ohms, R1 is 1 ohm, R2 is 1 ohm. So the turns ratio of the generator is 1. So this means that R2 prime is to R2, for example. So it's transformer, but the transformer with turns ratio 1. So we're given what the slip is. We know the generator is operating at a slip of -0.1. The generator is connected to this grid, 690 volts. So this means this is 690. So the resistance of the core is very high, so there's no parallel resistance to Xm. We're going to, right, so here saying I'm going to make this easier, I'm going to assume these currents are the same. Then let's compute a bunch of things, right? Let's compute the reactive power, the developed power, the power delivered to the grid, and the power factor at the generator terminals. Okay, so we want to do a bunch of basic sort of calculation based on this circuit. Okay, so let's look at our circuit. Okay, so this is our circuit. Now let's look at, do some calculations, right? So as an approximation, so here we're going to assume Im is 0, right? So the question says assume Im is 0. This is an assumption we often make in practice to make calculation a bit easier. So our circuit is VA1. R1 X1, x2, R2, variable resistance, R2S, 1 minus S. Okay, so this is our equivalent circuit. And then we want to compute a bunch of numbers out of the circuit. Okay. So the normal thing we do in our first calculation is, so let's keep this here. Let's keep this here. Let's say this is IRM, XM. Okay, so we're going to move this magnetizing branch. We're going to move the shunt to the beginning of the circuit. Okay, so question A says from the reactive power of the generator. Right, so this generator is producing some active power, but let's say what the reactive power is. Let's see what the reactive power is. So what is the first step if I want to find the reactive power? What is the first step we do here? Anybody? What's the first step? If I want to find the reactive power in this circuit, what's the first thing I find? Current, right? So the chance has current, right? So for all this kind of problems, the first step is let's find current. Okay, let's find IA. Okay, let's find IA. Okay, so let's find the current through the system. So let's say this is IA. Find this current. Okay, so this current is not very hard to find, right? Our current is basically given by the voltage over the equivalent, right? Voltage over the equivalent impedance. So to be precise, these are phasors. So let's write them in Phasor notation. Okay, these are phasors. So this is 690 angle 0 degrees, right? 690 angle 0 degrees. Angle 0 degrees over the resistance is R1 plus R2 plus R2S 1 minus S. If we can add all this plus J, the equivalent resistance is X1 plus X2. Okay, so this is what we have. Right? So we can plug in the numbers and do this calculation. So if you look at this equation, and it says the voltage is 690. What does 690 mean here? Is it line to line voltage or the line to neutral voltage? For this kind of three-phase. Okay, so here the generators connect to a 690 volt grid. Right, so for the voltage, should we use 690 or should we use something else? Right, so this is line to line. It's line to line. So when we compute the current, then here, let's say this is the phase current. Right, the reason is indexed by A. It basically says the current in phase A. So if this is the line-to-line current, then what I need to do is I need to convert this into, I cannot directly use 690 actually. What I need to use is I need to use this thing divided by √3. Okay, I need to, here this V, this needs to be aligned to neutral voltage. Okay, so it's not 690. It's not directly 690. Okay. So the easier way to do this, instead of doing all the sort of angle conversion and things like that, is basically to look at the magnitude of the current. Okay, we can look at the magnitude of the current. This is basically what we have. This is the magnitude, the line to neutral voltage, divided by R1 plus R2 plus R2S, 1 minus S, whole thing squared, plus X1 plus X2 squared. Okay, so let's directly look at the magnitude of this current. And if we do this through magnitude calculation, what we have is 690. To convert from line to line to line to neutral, as we divide by √3 in the magnitude. And then in the bottom, we have as R1 plus R2 over minus 0.1 squared plus X1 plus X2 squared. We get 41.25 amps. Okay. So the tricky thing here is to remember that the voltage almost always is given in line to line, right? But when we calculate something like IA, we're often computing the line to the phase current, right? The phase current. Okay, so remember to divide by √3. Okay, remember to divide by √3. Any question with finding the current? Okay, so this is the current, right? This is my current. And then the reactive power basically is given by 3 times IA squared X1 plus X2, right? So I have a current through two inductors plus Vm times Im, or Va times Im. Right, so I also have a shunt. I have a shunt at the beginning. So I have Va squared over Im. So let's try to say Va squared over Xm. Right, so I have a shunt. And now things in shunt, I have things in series. So I can plug in all those numbers. What I get is 3 times 41.25 squared times X1 plus X2, 3.5 plus 3 times 690 over √3 squared over 10. So I get the amount of reactive power as 65.70. 65.47 kilowatt. Okay, so this is my reactive power calculation. Basically, you're looking at all the elements that can consume reactive power, and then you just account for all of them. Any questions with this reactive power calculation? So if you have questions, please ask, right? You'll be seeing a lot of this in the next homework, and definitely on the midterm.
I'm a bit confused on before we were taking the grid voltage and then dividing by the resistances. I'm just confused about kind of the polarity of how we're doing that. I think it's a little, or if we look at the circuit, because we're taking the grid voltage and then dividing by that resistance. I would think the current we're solving for would be going the other way. Is that?
So let me draw the, so I think I drew the current the wrong way.
But then it's a generator, right? And is our resistance positive?
So no, the resistance is negative, right? Resistance is negative. This is negative.
Oh, okay. I
Right?
missed.
So R2 over S is negative, right?
Gotcha.
Yeah, it's negative. So
Makes sense. Thank you.
yeah, the polarity. So the way, which way I drew the current is actually, so here, this is the current magnitude. So let's be clear, this is magnitude, right? This is magnitude of the current, right? So because this is negative resistance, if you actually compute the complex current, you have a fairly large angle in the current itself. Okay, so here, for simplicity, I'm just computing the magnitude of the current. Okay. All right. Any other questions about this? The reactive power calculation, the current calculation? Okay, so we got the reactive power. Then the next one is a developed power. So the developed power, if you recall this equation, what happened to my, right? So this is our this is our sort of short equation here, right? So we can plug into that equation. Developed power is -3 times IA squared R2S 1 minus S. Okay, so we're going to plug S equal to minus 0.1 into this. So plugging everything in, we get -3 times 41.25 squared 1 over negative 0.1, 1 plus 0.1 because we're subtracting a negative number. This we get is 56.15 kilowatts. Okay. All right, so this is our developed power. Okay, this is our developed power. Any questions about this developed power? Okay, so if this is our developed power, then the power to the grid or the power output is just the power here. Subtract the losses we have, right? So I have a I squared R loss in the system, I squared R1, R2. So this is my developed power, subtract 3 times IA squared, R1 plus R2. Plugging all the numbers, what we get is 45.94 kilowatt. Okay, so this is just the developed power, subtract the thermal loss, subtract the sort of the active power loss on the, okay, subtract the active power loss. Okay, so D, now D is interesting, D is interesting. What is the power factor? Okay, what is the power factor? Maybe you could remember the equation for the power factor? All right, so the power factor is this is, so is this leading or lagging power factor? I think about this. I think about the power factor. So if you look at Q, right, is a generator generating Q or consuming reactive power? If you're an induction machine, right, we'll compute a Q, right? We'll basically compute the current through all the reactive elements, and that's reactive power. Okay. So who's supplying this reactive power? Is it the grid or is it my generator? Right, so who's supplying this reactive power? Why is it the grid supplying reactive power? Right, so the answer is correct. It is a grid supplying reactive power, but why? Right? Can I get reactive power out of my generator? Right, so let's go back to this our circuit, right? Circuit diagram. Can I get it out? Can I possibly get out this? Can I get any reactive power out of my generator? Right, so normally when you build a generator, you not only want active power but also reactive power, right? So why is it that the grid must supply reactive power for my generator to run? Why can't I not just run my own generator and supply reactive power? And sort of supply the reactive power that need to be consumed through these reactive elements. So let's look at this equation. Okay, this is VD. This is the current through the voltage source. Right, what's the phase between the current and voltage? Okay, so we're going to think of the generator as this developed voltage, right, as this sort of voltage source. Then if you look at the current produced by the voltage source, what's the phase between the voltage and current?
They're in phase.
They're 180 out of phase, right? Or yeah, they're 180 out of phase. But the problem with 180 out of phase is you cannot produce reactive power. Right? Right? So your active power you produce is, you produce active power, but the reactive power of these two being 180 out of phase is reactive power is 0. Right? So if you look at this, the power is 3, right? So let's look at, if we look at the complex power, the complex power, developed power is 3 VD IA 2 prime complex conjugate. Right? This is the complex power. But this is 3 times minus RD IA2 prime times, if I look at a complex conjugate, minus R2 prime over S, these are real numbers, right? These are all real numbers. 1 minus S is a real number. IA2 prime could be a complex number, could be a complex conjugate. I may need to take complex conjugate, this is fine. But this is a real number. Okay, this is a real number, right? Because IA2 prime is multiplied by IA2 prime conjugate. So this is the magnitude square. Everything else is real in this equation. Okay, there's no imaginary part out of this number. Okay, so this means this is no reactive power. Okay, this is no reactive power out of this thing. Okay, I cannot get a reactive power out of this source. Okay, just because my developed voltage is 180 out of phase with the developed current, or in phase with the developed current, depending how you count it. Right? But there's no immeasurable part out of this complex power. Okay? So then it's right. So all the reactive power needed, right? All the reactive power needed is basically supplied by the grid. Okay, this is supplied by the grid. Okay, this whole thing is supplied by the grid. Okay. So if you look at the power factor, basically what this gives you, this is a lagging power factor, right? Because there's a negative sign. You have a negative sign on the Q. So, and this is power factor as the cosine of the tangent inverse of Q over P. And this is 0.574. Okay, so you have a lagging power factor because your generator is consuming reactive power. Okay, so this is, for no way you can get reactive power out of this generator, right? Okay, so if this is the case, now let's imagine. So let's say you create a small system, let's say you make your type 1 wind turbine. Okay, let's say you have type 1 wind turbine. And so let's say you want to power something like your fridge. Okay, so if I build a type 1 wind turbine, can I power something like my fridge? Can I power a standalone load? Right, so let's say you want, you want to completely get off the grid. You build a house, and you build a type 1 turbine beside your house and connect both together. Okay, does this work? Can this work? Right, so because the type 1 turbine also consumes reactive power, and your load, if your load also consumes reactive power, you actually cannot directly just connect the turbine to the load. They're both consuming reactive power. You need to get reactive power out somewhere. Okay, so that's why type 1 turbine are not the best in a standalone system. Okay? Because somebody needs to provide Q. Okay? There's no Q in the system. So yeah, go ahead.
Would it be possible to have one of these in a standalone system? Because you need power to the stator windings in order to have it work as a generator at all, right?
You need a synchronous frequency, right? You don't necessarily need power, right? You basically need a frequency. Also, so if you have, somehow you can provide the frequency with very little power, it could work. But that's also a problem, right? Who's going to provide a synchronous frequency, right? So your fridge is not going to provide synchronous frequency, right? So that's why type 1 turbine, I guess, yeah, for both the reasons that you need a synchronous frequency and you need reactive power, as it's not going to work in a standalone system. It cannot be the main thing. It cannot be sort of the main power provider in the system. Okay, it doesn't do it cannot maintain frequency. You need outside frequency. It cannot provide reactive power. Okay, so if you listen to the talk earlier this morning, this thing is not very grid forming at all. Okay, so this is not something that will support your grid. It's not something that will keep the grid going. These are used basically say I have ample reactive power. My grid is fairly stiff, can give you a good synchronous frequency, and these are just generating power. Okay, you have generating active power. Okay. But that's why they're relatively smaller. They're sort of first generation. But so now their drawback is sort of clear out of this. Right? So that's something to remember, right? Why, if you ever got to a situation a couple class later, thinking about why are we looking at all this complicated, electronics around these things? Why not just put a induction motor, just let it go? Right. So there's 2 reasons, right? Synchronous frequency and reactive power. Okay? In fact, if in the earlier days of wind turbine design, you spend a lot of time thinking about reactive power. You try very hard to get this reactive power from somewhere else. Right? So you have variable capacitors, you have stator comps, you have different setups. All of those is used to provide this reactive power. Okay, so this is something to keep in mind. Right. So this generator does provide active power fine, but does not provide reactive power. So let's do another example, right, to remind ourselves what the induction generator, how it works. So this is more of putting everything together. Right, so we'll start from the beginning, right? We'll say, I have a wind turbine with 25-meter long blades. I have a far stream wind speed being 15 meters per second. And the coefficient performance is 30% as the operational pitch angle. Okay, so this is the turbine part, right? This is a blade part of the turbine. I have a 6-pole machine, okay? A 6-pole machine. The mechanical efficiency is 85%, and the electrical efficiency is 90%. Those sort of various losses in the system. We want to find the power captured by the blade, the slip, the power to the stator, output electric power, the stator loss, or rotor loss, and so on. Okay, so this is all the things we want to find. Okay, so let's go through this equation. So let's first do the power captured by the blade. right? So part A, my power captured by the blade is, so the wind power I have, or PW for wind, half delta, the area of the blade, times the wind speed cubed, wind speed cubed. And then we'll multiply, we'll look at, we'll put CP later into this. And so now let's just compute the power in the wind without multiplying by the coefficient of performance. All right, so this is half, I'm gonna assume delta being 1, 25 squared times 15 cubed. So this is 3.31 megawatts of power. This is sort of the power in the wind. We haven't multiplied by CP yet, so we'll do that later. We'll look at the power delivered to the stator. So this is our power. And then let's look at our slip. So what is the synchronous frequency here? What is the synchronous speed here? Of the 6-pole motor. And it's rotating at 1260 RPM. What's the synchronous speed here? Here, yeah, you actually don't need to use the pole equation, right? So this is a, since we know the slip gets small and there's only that, so many synchronous speed. So if your speed of the generator is 1260, the synchronous speed has to be 1200 RPM. It has to be 1200 RPM. So this is the closest synchronous speed we have. Okay, so if you ever see this kind of question on the homework, on the exam, that doesn't give you a number of poles, but says the machine is rotating at 1260 RPM, you expect to know what the synchronous speed is. Okay, you expect to be able to recognize what the synchronous speed is. Part C. So let's look at what the power to the stator is. Okay, so let's look at the power to the stator is. So the power to the stator is basically PW multiplied by CP, right? This multiplied by CP. This gives us the power to the rotor. Okay, this is the power to the rotor. This is power to the rotor. This multiplied by the mechanical efficiency. This is the developed power. Right, so I have the wind power. I multiply by CP to see how much of that I can extract. That goes into rotating power. There's a mechanical efficiency. So I multiply by the mechanical efficiency to get the developed power. Okay, so the developed power is my 3.31 multiplied by CP. CP 30%. Multiplied by 0.85, my mechanical efficiency. This is my developed power. This is 844.05 kilowatts. Then what is the power delivered to the stator? Anybody remember what's the power delivered to the stator? Right. So you look at our equivalent circuit. This is the grid side, VA. This is my grid side. There are some losses around here. Right? So I know the power, this developed power, this is PD. Okay, so the stator power is we want to compute how much of this power gets to here. We want to compute how much of this power gets to here. Okay. So this is called the stator power. This is called the air gap power. This is because I have a rotor. This is air gap. And this is the stator. Okay. So often what we say by the power delivered to the stator is a power that I have in the air gap. Anybody remember this equation? What's the relation between PG and PD? Anybody remember this? Right. So there's an equation, and the equation is this is PD over 1 minus S. Okay, so next class we'll go through all these equations again. But this is just a reminder, there's a bunch of equations here. Okay, so we turn out you basically the power you lose is the power going through this resistor, right? This R2 resistor, this R2 prime resistor. And turns out with some algebraic manipulations, you have the power to the air gap as PD over 1 minus S. And forgot to compute S here. So S, the slip, is N minus NS over NS, 1260, 1200, 1200, 05. Right, so this is my air gap power. So this is a 44.05, 1 minus 0.05. So combine them together, we get 803.86 kilowatt. Okay, so I lost some power going through this R2 prime resistor, right? So I delivered 803.86 kilowatts of power to the stator. Right, so the output electric power is basically the air gap power multiplied by 0.9, right? So we lose another 0.9 out of the electrical efficiency. So what I have is power out is 0.9 times the power in the air gap. This gets us to 759.65 kilowatts. Okay, so we have this being the total power output. Okay, so then we can compute sort of the different various loss mechanisms we have in here. Right, so our loss mechanism is, for example, we have the loss in copper 1. This is the air gap multiplied out, right? So you lose this power in R1. So subtracting this power gives you the stator loss as 44.21 kilowatts. So this is stator loss. Then PG, the rotor loss is PD minus PG. This is 40.2 kilowatts. So this is the rotor loss. And then the overall efficiency this is basically P out divided by the total power I have as wind, right? So I lost a bunch of divided by total power, and this we get is about 22%. Okay, 20% of loss. Okay. So this question is basically just a reminder of different type of equations we have. Next class we'll go to a lot more detail. Okay, we'll go through all these equations again. We'll remind ourselves, where we got these equations. We'll basically look at how do we develop these equations? What kind of loss mechanisms are there? We'll basically do sort of this. We'll list all the possible equations you can have for induction motors. Then we'll look at how we correct for some of the issues. basically, right? So, what about reactive power? What about the stability of the rotor and things like this? Okay, so that's what we'll do next class. All right, so let's end here today, and I'll see you on Thursday.